Hello, everyone, and welcome back to NLP for All, our workshop series where we primarily discuss how to use natural language processing and speech technology tools in order to work with data that is in the form of text or more recently in the form of speech. In today's session, we will be specifically looking at speech to text with Whisper AI, which is a fairly popular open source free platform for generating high quality multilingual transcriptions. We'll be looking at how this technology was developed and what are some common use cases, and most importantly, how do we interpret and use our output. So as always, the first thing that we want to do is navigate to the GitHub repository. This is the github.com UA Data Lab NLP/NLP-speech, which is where all of our notebooks and all of our materials lives. If you scroll all the way down the calendar to today's date, you'll see the name of the workshop and a link to the Colab notebook that we'll be using today. Now, if you click on this, it'll take you straight to the notebook. And on the page where the notebook lives, you will see a button which says Open in Colab. I'd like you to click on this. This will open your instance of today's notebook, which will be saved to your Google account. And so you can feel free to make changes to the notebook and run the code along. The first thing that we want to do today, because we are working with large models, is we want to change our runtime and make sure that we are connected to a GPU. So if you look at the top right corner, it will there you'll have the option to connect. It might say in your case, it might say connecting while it's looking for something for you. In case it doesn't say GPU, make sure that you click on change runtime type and click on the T4 GPU. Okay. So I'm not going to do this right now, just in the interest of saving compute, but I invite you to do it. And once you're done, in the interest of time, I'd like you to click on runtime and click on run all. What this does is it sets up all of the code in the background while I go over the theoretical points for today's session, so that when we're ready to actually run the code and look at the output, it's ready and waiting for us. All right. So let me go over my checklist, make sure I have hit all my points. Give me one quick second. All right. Yeah, that's good. Okay. So all right. Let's look at some terminology for working with speech to text. First of all, speech to text is a task where we take a file, which could be an MP3 file, it could be a WAV file, it could be audio in any of the different formats, which is used as the input. We run it through a pipeline, which connects it to a bunch of speech and language models. And ultimately, the output is human readable words that are returned in some kind of a text file, right? This output could be just a .txt file, which just has all the words that the system thinks existed in the audio, or we could have a transcription file, or we could have a subtitle file. And we'll be looking at this a little bit more today. First, what is a transcript? It's a text file which has all the text that corresponds to an audio file. Next, closed captions. If you have turned CC closed captions on for this video, you'll notice that as I speak, Zoom is transcribing the audio for me. This is happening in almost real time. There might be a couple of seconds delay. This is the closed caption file. once this video is done, and in case you're viewing this on YouTube and you click on the subtitles, you'll notice that as I speak, there is a corresponding line of text that appears at the bottom of the file, bottom of the video. This is the subtitle file, which has basically the start and end time for every sentence or every turn that I take in this audio file, and it's being displayed in a real time. Finally, we'll be looking at word error rate. This is a metric where we use it to find out how many mistakes a audio transcription system is making. The output for a WR metric is usually WER metric is usually a percentage, which tells us how many mistakes were made for every 100 words of transcription. Right. Next, when it comes to transcription, subtitling, captioning, our text files are often saved in a variety of different formats. Most of these formats are pretty interchangeable, but it's useful to know the difference between the different formats. So you might see if you, for example, have ever turned on transcription for a Zoom recording or any other kind of meeting recording, you'll notice that when you leave, you might have a .vtt file. If you watch movies and you need the subtitle file, you'll notice that many of them are in the .srt format. We also have text files and JSON files and text grids. Essentially, any transcription format is something that makes sure that the start time, end time, and transcript are all aligned in some way, so that a system can knows when when someone started saying something and when someone ended saying something. Now, next, I have a couple of examples of what these different files look like. VTT or web VTT, for example, will typically look like this. You'll notice that there's a little arrow that between a start time and end time. Then there is a line break. And then on the next line, we have the transcript. And between any two turns, we have a space. So it's just the format that WebVTT uses. And when a system processes a .vtt file, it uses all of these spaces and characters in order to process it. The subtitle files look a little bit different. The turns are typically numbered. And we again have start time and end time. When it comes to JSON files, you'll notice that there are curly brackets that are kind of collecting information that logically belongs together. We have keywords like start and end and text in order to denote the different components inside each element. And most of this is, and all of this is saved with a .json output extension, right? Some other less popular or lesser known formats include text grids, which are used by speech processing software like Pratt. These will save all of the data with, it's more wordy, it's more, the numbers look a little bit different. You might even have the transcript, which is, rather than being at a turn level or a word level, we might even have them at the character level. So depending on how much granularity a person needs. Ultimately, what we want from our transcript file, we want the content, and depending on how we want to use it, we might also want to time align it with the speech that is in our audio file, right? When we use this for our NLP pipeline, it's very important to know which output format our transcripts are in. It's also important to understand what output or input format the NLP pipeline is asking, and make sure that all of our both ends are aligned. So now that we have our transcript files, the next question would be, what do we use transcription for? One of the most important use cases for producing audio transcripts is accessibility. We want to make sure that our audio is not just available in one modality, but in more than one. When we add captions to our files, it makes sure that in case the audio is degraded or a person's in case we have people who require accessibility, the transcripts are another way in which they can follow the audio along. Again, this is a universal accessibility thing. It's about making sure we never know when our transcripts can be valuable for an audio file. So it's a good idea to, by default, make sure that the captions or transcripts are available. Next, when we convert our audio stream into text stream, this means that our output can be used by assistants. It can be used by hands-free applications. So if we convert our audio to text, that's how Siri or any of your voice assistants are processing what you're saying. You may have noticed that when you speak into a voice assistant, especially one that's on a handheld device, it displays the words that you said so that you are able to make sure that the text is being understood correctly by the system. And once the audio has been converted into text, that's how the language model in the back end of any voice assistant works. Next, when we have downstream NLP tasks that we've been discussing throughout our workshop series today, it could be semantic search, it could be um, identification of keywords or any other NLP task. It could be a sentiment analysis. We want to make sure that our NLP tasks are not limited by modality. And so when we are able to convert our audio stream into text, this gives us more data to work with. How can you generate transcripts? So first, besides the one Whisper that we will be looking at today, SpeechBrain and Koki are two other very popular free software which have many high quality, well-trained language models across multiple languages. These can be used for transcription, or as in this case, the task is speech to text. Besides the free, more complex and coding required software, there's also free, there's also paid options that we tend to use every day. The most popular being Zoom, which happens to be a paid service but is free for UFA affiliates. If at the end of this meeting, or if you go and at the bottom of the Zoom bar, if you click on the options and click on transcript, you'll notice that it generates a .txt file. So it's definitely free for us, but depending on the kind of enterprise account that one may have, it may not be free for everybody. Besides Zoom, AWS, which is the Amazon service, as well as Google, both have transcription services available that use their language models. Of course, these are paid, and the cost can vary depending on the size of the audio that we're processing. So just in case you're wondering, or if you've never worked with Zoom transcripts and captions before, I have a couple of steps here for how to do it. Zoom transcription is good for non-private settings. So in case, because Zoom transcripts are by default are saved on the Zoom cloud, the transcripts, it's more useful if the audio that you're using is does not need any kind of privacy. Zoom generates a .vtt file which has the timestamps. It also generates a .txt file where it's just summarizing, where it's only saving the text that is being spoken. It ignores which speaker said what. It also removes false starts, and it removes sounds like that are filler sounds. And again, Zoom gives you the option to choose between multiple languages, and it's also auto-detecting languages. So if I stop speaking in English and start speaking in a different language, the captioning system will ask me if I'd like to change the default language that I chose at the beginning of my audio. So in case you're interested in working with Zoom transcripts, there are a couple of options here. There are a couple of links here which provide more how-tos on running Zoom. And I'll give you a few seconds to connect and look at the links and make sure that you have access to these options. Now, one of the multiple use cases for speech to text is using the output of our STT system in order to run downstream NLP tasks. So some popular NLP tasks include summarization of conversations and automatic note taking. You may have noticed that Zoom AI now provides these options. And essentially what it's doing is it's taking all of our audio that we're generating in the file. It's extracting the text from it, and it's making sure that all of the long form content is broken down, and the key information inside that information is inside all of that audio is provided in the form of shorter spans of text. You can also use the output of STT for topic analysis to understand what is being said. We might also want to do named entity recognition. If you'd like to learn more about it, I invite you to check out the first workshop in this series. We might also want to run a few alternate tasks, such as trying to understand who is the dominant speaker in a given recording or in a given audio, and also assess conversational quality. Are people comfortable talking to each other? Are there long periods of silence? Are, this also includes sentiment analysis. So, are people able to talk to each other? What are their sentiments and emotional state when they're having these conversations? So these are examples of some of the downstream NLP tasks that we could run. Next, how did we get here? What were the technological advancements or changes which got us to a point where automatic speech recognition went from just analyzing an audio file to actually generating viable and useful text data that was high quality enough to be used in near real time? First, it's important to distinguish between the kind of models that these pipelines use. We have language models, which are essentially looking at the output of an SCT system. They're going to need text. They're going to need it with some kind of sequence. And what a language model essentially does is it looks at a string of words, and it's trying to understand what the likelihood is of one word being next to another. So this is how it develops the capability to generate new text that it's never seen before from an existing corpus. Now this allows it to generate this can be used by the user who provides input prompts and gets information as the output. Language models are trained on large text corpora. They develop an understanding of grammar, context, and semantics. And this is the primary model that we use in most of our natural language processing systems. Speech models are primarily focusing on the spoken language. What they're doing is they're taking an audio signal. This could have data in the frequency domain, in the time domain, and it's finding a way to convert this into text. It can, besides the speech to text and transcription systems, we can also use our speech models for things like language detection, dialect detection, voice activity detection. So who is speaking when. We might use it for speaker identification and authorization. We might use it to listen to a stream of audio and separate it out based on who was speaking when. And it's also used for audio source detection. So is there a bird chirping in the background? Is there traffic noise? So all of that is also done by basically speech systems. And at its core, a speech model is working with linguistic units. These could be phones or phonemes. It could be putting these together in order to assess words. It could also be working at the tone level. And it's also identifying and evaluating non-speech sounds, so in the background. And why primarily our speech models are helping us not just extract what was being said, but it's also giving us information about how something is being said. So a speech model can give us information about the tone, about prosody, it's telling us about accents, it's telling us about pronunciation, which are all nuances that a text model or a language model is not going to be able to extract from text, right? Now, as far as the state of the art goes, both domains are currently using the transformer architecture. If you'd like to learn a little bit more about this, we have a session in this series on transformers. And the objective here is to predict a following sequence for a given unit of data. Now, with speech models, the concern is to take input audio and turn it into some kind of a mathematical representation, and then try and understand what were the sounds that exist in a given unit of audio. The language models are more focused on extracting meaning from a given text corpus and then using that meaning for other tasks. Now, because the human communication specifically tends to have an objective of exchanging information and communicating with our partner, these models, while looking at separate kinds of data, they're both fundamentally working with human communication. And so they're not, they are working in tandem and they're working together. And what is a person's desire to say is going to impact how they say it. And so speech models are, it's very important for speech models to have the support of language models and vice versa. So these are not completely separate ways of looking at language. Now, specifically, when it comes to acoustic processing and speech modeling, one of the major breakthroughs happened in 2020 when Facebook AI or Meta AI released the Wave 2 VEC 2.0 model. This model was specifically aimed at automatic speech recognition. When this training was conducted, it used a whole bunch of unlabeled audio data. So this is just chunks of audio where the model wasn't really being told what it's looking at. And all of these representations of speech signals from all of these thousands of unlabeled audio data units were provided to the model. And then once the model had access to all of its data, it tries to basically understand and predict a given representation for an audio that it's never seen before from audio that it's seen before. And once the model was ready, they fine-tuned it on smaller concentrated data sets to make sure that different automatic speech recognition tasks could be performed better. So a model that's fine-tuned for voice activity detection might require different parameters than a model that's being fine-tuned for machine translation. And so because of the two-step process and because of the kind of architecture that was used and specifically the rich data, all of this really helped us with a model that performed speech recognition at very, very high degrees of accuracy. This particular architecture was then used by OpenAI to develop its web-scale supervised pre-training for speech recognition. A mouthful, but now it's more popularly known as Whisper AI. In their use of previous technology and the kind of, they also made some advancements, but if you try and read the Whisper AI paper, you'll notice that a lot of this is pretty much a lot of this information on how they built their model is not public. So broadly speaking, they used 680,000 hours of training data that was not just in English, but in multiple languages. Because they were building a transcription service, they provided it with English transcripts. They provided audio alongside translation, so English as well as a different language. They also provided the transcription in a variety of different scripts, and they made sure that their audio data set had audio that had a variety of different kinds of background noises. So everything from music and traffic blaring in the background to high quality recordings. So once their data was sent through through their model, the output was a bunch of different NLP tasks such as machine translation as well as transcription. And so the model was able to do a whole bunch of things. And the focus was always on building a system that is capable of multiple tasks. So this is a rather complicated image, but broadly speaking, the input is audio, the output is text, right? Now, it did use a transformer model. A lot of this model's objective was to map the utterance to the transcription and make sure that it's mapping to transcription not in just one language, but multiple languages. Another advantage of using Whisper AI is that you can set it up in your own computer so long as you have a GPU system. It does work on CPU, but it's extremely slow. You don't need to send and receive data through a cloud or a text, so you don't need to interface or upload your audio to any place. The training data is very diverse, which is great for your audio, which could have its own constraints. And because of the way the task is set up, it works for a whole bunch of tasks and not just one. And it's powerful primarily besides the diversity of data. It's also the architecture, which makes it really great, and the objectives of the model's tasks, which include multilingual speech recognition. It's trying to identify the language as it listens to the audio, speech translation, spoken language identification, and voice activity detection, which are all simple tasks that we might want to do when it comes to audio data. And it's also very easy to set up and process, and you can build it within a Python pipeline, or you can run it in your command line, and we'll see examples of it. There's a little bit about the kind of audio and processing that's provided here. I'll give you a second to just go over it and get a sense of the model for yourself. All right. Next, I will move to the next part of our workshop where I will demonstrate how Whisper is set up and run. The first thing that we want to do is we want to make sure that Whisper is downloaded and loaded. And for this, I'm just going to use the GitHub repository that OpenAI has for Whisper. And I'd like you to go ahead and just run the code. I have a couple of setup options here, which make sure that you're connected to the right system. And for today's example, we'll also be downloading a few audio files, and these are all in MP3. I have 3 files in English and 1 in Korean, so we can compare the machine translation task. And once your files are ready, you should be able to play them over here, and let's see what that sounds like.
Mary had a little lamb. Its fleece was white as snow.
Right. So if you click on the play button, all of your audio will play for you. And if your system was set up correctly, then that's what it should look like. Now, the next part, if you did hit runtime and clicked on run all, then all of your installation steps should already be done. So I would tell you not to run it again. And if you are ready with the system, go ahead and simply hit play on the code chunk, which says Whisper help. If you're able to run this correctly, you'll notice that it prints out a whole bunch of options, text that many of which start with a dash dash. So this just tells you this just tells you how to use and build a Whisper command. What are the user options that are available? And so you have help, you have model, device output, output format, and we'll be going over some of the important options that you might need to set. Something worth remembering is the language option. So all of the different languages that Whisper AI is able to process all have their own 2-letter codes. English is EN, and in case you have any questions about what letters correspond to which language, you can simply you can simply Google this and make sure that you have the right language code. Now, besides the 2-letter characters, Whisper also allows you to enter the name of the entire language. And I think if I remember correctly, it is case sensitive. So all you have to do is simply click on Whisper help and just keep scrolling and find the language, the name of the language, so that you can use it correctly. Now, if all of this is set up for you, the next thing that we want to do is we want to make sure that we're connected to a GPU, and that's what the NVIDIA-SMI does. If you are connected to a GPU, you should, this is what your output should look like. If your output doesn't look like this, I'd like you to make sure that your runtime is changed to GPU. And the simplest step that we can run is transcribe a given audio. And this is what the command looks like. This is a command line example, and I have added little slashes at the end of every line here. This is just to, these are just to include line breaks so that my command is more readable. If I do not include these hyphens and simply click enter, then my code is going to show an error. For this first run, I've chosen the medium-sized model. I've let Whisper know that the task is to transcribe. I've asked it to save the output to a directory called Mary-transcription. I've told it that I want all the output formats, and I'd also like word-level timestamps, right? So I want to know when each word was uttered. Having done this, if you scroll and look at the output, you'll notice that the text is being saved here, is being printed here. And if you click on the little file icon, you'll notice that there's a little folder called Mary_transcription. And if you click on any of these formats, like except txt, you'll see on the right, a new little window will open, and this has your transcripts, right? Now, each of these files is going to look a little bit different. So you can take a look at what the different output files, options look like. And I'm just going to go ahead and close this so that I can continue. All right. Now, I have a few other examples here as well. The file allstar.mp3 is longer than the one that we have. This one, the first one is approximately, I want to say 8 seconds. This one, the next one is going to be a little longer. So if you're hitting play on this, I invite you to wait for a few seconds to make sure that everything is run correctly. And while this runs, I'm just gonna go ahead and explain the next task that you can conduct, which is speech translation. Now, in both of the first examples, we have our example audio is in English. And so our output is simply the text with timestamps. But what if our audio is not in English? Is there something else that we can do? So if you look at the Cupid_50_50_ Korean version file, this is a Korean song. It has a lot of music and percussion in the background. It also has text. And in this case, Whisper is going to be doing a whole bunch of things. It's going to first isolate the audio stream, the speech stream from all the non-speech streams. The next thing it's going to do is it's going to transcribe it for us. And in this case, I set the task as translate. And if you look at my previous code block, the task is transcribe. So in this case, I'm just asking Whisper to translate this for me. And by default, it's going to translate from Korean to English. And if you click on the play button, you'll also notice the second thing that I did was I set the output format to SRT. So I told Whisper that I don't want VTT. I don't want you to save the content for me in a whole bunch of formats. Just give me an SRT file, right? And so if you click play, this particular run will take a little bit of time. And you'll notice that for every audio chunk, the text is available in English. Now, if you do speak Korean, I invite you to assess the translation and let me know what it's like. Another thing that I invite you to do is I go ahead and copy everything that's here. You can create a new code chunk and change the task from translate to transcribe, right? So we're going to, instead of getting a translation, I'm going to ask Whisper to transcribe it for me. And I'm also changing the name of the folder so that it's saved in a different place. And go ahead and click play and see what happens. And while this system is running, it'll generate a couple of lines for you at the bottom. And it's going to take a few seconds. So I will let it run and I'll go on with my explanation and come back to this output in a few minutes. The next thing that we want to do now that we have a Whisper running in an isolated manner, we might want to invoke Whisper, and we might want to actually incorporate it into a NLP task pipeline or a text processing pipeline that we've set up for us in, say, Python. So in this case, we want the output that comes from Whisper to be used in our downstream code. And so we want to make sure that it's available to the rest of our code. So in this example, I'm going to run Whisper inside Python, right? So the first thing in our is we have a audio processing system set up over here. And I want to make sure that in this pipeline, the next thing that it's doing is it's actually transcribing. So in this case, we've set up a Python function for transcribing audio. It's going to process the audio. It's going to extract the spectral information from our audio, and it's going to pass this down to Whisper. And all of this is going to happen inside Python so that the output is saved in a variable that we can then call. Right. So if you try and click these code blocks, you'll notice that I'm able to use the print statement to print it. Now that you have all of this in string output in your Python system, you can save it to a file, or you can use NLTK or any of our or Spacey or any of the NLP tools to process this further. Now that I'm going to take a second to just show you the output of our Korean transcription before we move on. And you'll notice that it's a mix of the Korean script and Roman script. So wherever it's detected an English word, it's set this up in English. And wherever it thinks that there is a Korean being spoken, the transcription is in Korean. So very bilingual. It's also very friendly with bilingual transcription as well as monolingual transcription. So I invite you to try it on any other language that you speak and see how the performance is. Okay. Now back to our pipeline. The next thing that we might want to do is set up Whisper AI so that it can be used by someone who say isn't so familiar with programming. And so in this case, I'm going to use a little web UI toolkit that's going to invoke Whisper and Python in the background. And it's going to give me a little user-friendly website where our user can upload a piece of audio and run their system. Right. So again, in this case, we're going to use Radio. This might take a few seconds to set up. I hope that in case you've already set this up, then please run the gr.interface system and save time. I'm going to wait for the code to run and give it a couple of seconds. Transcribe is not defined. Hold on. Okay, just give me a second. I'm gonna make sure that my Python code is also set up. Whisper. Let me set up Whisper again, make sure it's available. Hold on. Okay. What is not defined. Okay, I'm just gonna quickly do a run all to make sure that all of my code is running correctly. While this happens, I will demonstrate what the UI looks like. I'm gonna go back to my notebook where I saved a run for myself just in case we run into trouble today. And if your code, if you have done a run all, things should work for you pretty smoothly. In my case, you will notice that once you finish running the gr.interface, it's going to give you a little public URL. This is going to help you if you click on this on the URL over here. It's going to open another web page where it's going to allow you to upload or record audio using your system, and it will transcribe all of that audio for you in real time. That's essentially what we're telling it to do here. We're asking it to run the transcribe function that we wrote in our previous code block. And once the function is made available, it's going to open up Whisper and it's going to run the function for us. Okay. Now, let me see if where I am with my code. It's going to take a few seconds. So while this happens, I'm going to go ahead and look at what I have next. Since we are on the subject of running NLP pipelines, the next something that we might want to do is visualize the text that is being outputted by our system. So we have text. We might want to ask questions like, what is being said in this audio? Is there a way for me to visualize the text and understand it better? And so for the visualization, I'm going to use word clouds today. If you're not familiar with the word cloud, I will explain. In the code for the word cloud, the first thing that it's doing is it's going to look at our file system, and it's going to go into the all-star directory, and it's going to pull up the .txt file. Now, if you double click on any of the .txt file, you'll notice that this doesn't contain any timestamps. It just has each of the turns that the ASR system identified are just simply printed here, one line at a time, right? So it's just text. And if it is text, that means that our NLP toolkits will be able to use it correctly. Okay. So give me one quick second. Let me just see where my system is at. Okay. So I'm gonna quickly pause the run and okay, thank you. And I'm going to go down and look at our visualization. Now, for this example, I'm going to open up the allstar.txt file, and I'm going to look into it and see if there's any text in there. So if you do click play, instead of running the first 20 words, you could run the first, instead of printing the first 20 characters, you could print the first 100 characters, see what happens. Okay, and the next thing that I want to do is I want to import my libraries. For this demonstration, I'm going to use the NLTK library, which is a natural language toolkit. In case you're interested in learning more about the NLTK library, I invite you to check out the text pre-processing session in this workshop series. Another new system that we're going to use, library that we're using today, is the word cloud library, which is going to generate the word cloud for us. We're also going to use matplotlib just to plot our system. And there are a few other libraries here. I'll explain as I proceed. Now, in order to correctly evaluate the text that's being outputted by our system, we might ask ourselves the question, if we want to understand what are the frequent words that a system is using, we might want to make sure that our system is not confused by stop words. Now, in English, a word like the or tends to be more frequent than a word like go or stop. And so the first thing that we want to do is make sure that our system is not confused by these words, which are called stop words. And we're going to use the NLTK library in order to first download and set up a list of stop words for us. Now, if you are able to run this code block, this will print out all of the words in the NLTK stop word list. You'll notice a lot of WH words. There's a lot of pronouns, there's articles. So all of these are words which are very important from a grammatical and syntactic point of view, but they don't actually contain a lot of information. So once we're able to set up our stop word list, we're going to run this word cloud in two different ways. The first way is we're going to simply pre-process all the text in our transcript and just generate a word cloud which tells us how frequent a given word is. In the next example, we're going to actually remove all the stop words, and we're going to run this again. And in this case, what we're asking is, hey, what are the salient meaning-carrying words in our transcript, and how often do we see them, right? So if you're able to run this code and pretty print the output, you'll notice that in the first case where all the stop words have been preserved, the text is going to look very different from the second case where a whole bunch of words are suddenly missing. And the words that have been taken out are going to correspond with the stop word list over here. So in anytime you're conducting a natural language task, it's always important to assess if you need to keep your stop words or remove them. The next thing, once we have our words and each of these words is going to repeat a whole bunch of times, the next thing that we want to do is examine what is being said in this particular audio. And so I've generated the word cloud. This is what a word cloud looks like. It'll print all of the words that the system sees. There is a way to, in this case, if you look at the two word clouds that it sets up, if you look at the second one, you'll notice that there are some words which are larger in size than others. These are the words that reoccur in the text more times than others. And this is just a simple visual way to understand, broadly speaking, what's being said in an audio, right? So there are two examples here. Feel free to try this with other examples. Note that the stop word library is English specific. So if you change your language, you might need a different system, right? Next, now that we have our transcripts and now that everything's been set up, the next thing that we want to do, and the final thing that I'll be discussing today, is evaluating the output of our system. So in order to assess how well our speech-to-text system is doing, one of the measurements that we use is called word error rate. The word error rate essentially tells us if the difference, it tells us how many words a speech-to-text system got wrong for every 100 words, right? So if the word error rate is very high, this means that the model is not doing a good job transcribing your text. If the word error rate is very low, this is good news for us. And broadly, when it comes to how is this comparison made, we might, in this case, we need some gold transcripts. Usually these are human-generated transcripts, so you get a human being to actually type out what text they see in an audio. And then we compare our model performance and we try to see what the difference is between the gold transcript and the automatically generated transcript. So for this demonstration, we'll be using the GIWER Python package. I have a few setup options and I've reinstalled Git here, but it would be, I think you can, in case your setup works, then you can go ahead and look at the code where we are actually running our system. For today's example, I'm going to use a large transcription database, which contains human transcripts. And what we're going to do is for all of the thousands of sentences in this data set, we're going to ask Whisper to transcribe the audio that it sees in each audio file in this data set. And then we're going to compare the human generated transcripts against the Whisper generated transcripts that we just produced. So as you run the code, the first important thing is to look at the table that gets generated. So here we have, we've just taken our Whisper output and we've taken our output that comes directly from the database that we just downloaded. And we're just trying to see how different they are or how similar they are. And if you just look at it, just visually speaking, you'll see that there are some words which are transcribed correctly, but there are some other words where the transcription's a bit funky. So in this case, the gold transcript is has the word stuff, but here Whisper thinks that it heard Stafford. So immediately, it's an immediate error that it encountered. And overall, you can take a quick visual look at this. Some of the transcription differences are just quirks. So for example, here Whisper decided to use 10 to denote the word 10, but the gold transcript had the word TEN. So just in order to make sure that our model is like robust against such errors, we're giving it lots and lots of sentences so that we have a good measure. And in this case, our data set has 2,620 audio files, so that's quite a big number. And if we run the WER system, what it's going to do is the first thing it's going to do is it's going to make sure that all of the audio is case matched. So we don't want any case related confusion. The human generated gold transcripts are all uppercase. This is not true for Whisper, so we want to make sure that this doesn't confuse our system. And so the first thing that we're going to do is we're going to make sure that all of our text has the same case and there aren't too many issues on that front. The next thing that we're going to do is actually calculate the word error rate. And so it's going to go and look at all of these 2,000 odd sentences, and it's going to assess how many differences at the word level it sees between the human generated gold transcript and the Whisper generated AI transcript. And the answer for this particular data set is 4.27%. So for every 100 words, the system makes approximately 4 to 5 mistakes. And depending on your use case, you can decide if 4.27% for English is a good enough metric. And if you're satisfied, then Whisper is a good use case for you. Otherwise, there are other STT systems that you can use which have a higher performance level, completely up to you. If you'd like to learn a little bit more about Whisper, the paper is a good option. Otherwise, there's also a few other resources. Most of the code that I use today comes from the Whisper documentation, which is really good, and I invite you to check it out. And if you have any questions, feel free to reach out to the Data Science Institute. And thank you so much for your attention.